We are going to start with some of the basic properties that describe waves. So we're all fairly used to seeing a fairly typical picture of something that mainly looks like a water wave is usually the association that people start out with. A sort of equilibrium line in the middle here. I'll label that. Which would be the natural resting position. If there was no wave passing through, you can imagine that this is water, or you can imagine that this is a slinky that someone is waving side to side on the floor. And in previous years, you probably would have encountered the words crest and trough, trough meaning that very lowest position, and crest meaning the very highest position, that displacement from equilibrium. That works fairly well with something like water because there is that natural up and down. But when we're looking at things like slinkies or things like sound or light, that doesn't really make as much sense, crest and trough, as being different. If you turn your head over upside down, then you would label them the opposite way. So they're not really terribly relevant words. They make sense as a picture in thinking about water, but that's about it. If we are going to describe some of the physical properties, though, of the wave, the easiest one to start with, because I've already alluded to it, is that displacement from equilibrium, and that is the amplitude of that wave. And I'm going to define it as the maximum displacement from the equilibrium position. Because that is a displacement, I would measure that in meters. In terms of a symbol for the amplitude, sometimes you see this written as an uppercase A for amplitude. Sometimes you see this, depending on the textbook or the source, written as an X with a subscript of a 0 or X naught, which is just an old-fashioned fancy way of saying 0. So it depends a little bit on the source of where you would, how you would see that referred to. The next major property that we can get just from looking at a wave directly and taking measurements from it is that wavelength. And I hate to use a definition that has those two words in it, but when it comes down to it, it is really the length of one wave. And what that means is the distance along the wave from one point to the same point where the pattern starts to repeat itself. So if I start here, the moment where I'm at the beginning of a new cycle would be right there. Or if I start at a crest, the point where the pattern begins to repeat itself would be that next crest. So I can pick any point on my wave and use it to define a wavelength if I keep that in mind, that it's just the horizontal distance or the distance along the wave until the pattern repeats. Since this is a length, it is also measured in meters. And for a symbol, it gets a Greek letter lambda. Lambda makes the L sound in Greek, but we've already used L to mean a generic length, so we use lambda for the wavelength. So for the next two properties, we would need something a little more than a ruler to directly measure them, but if we added a stopwatch to our arsenal, we can start talking about the amount of time that it takes to repeat some of these cycles. So that would be defined as the period of the wave. We're going to have two very closely related definitions here. So the period is the time for one complete cycle. So that could be from a crest to the next crest, or it could be from a trough to the next trough, or like my first wavelength here, from one equilibrium point to the next one that's at the same point in that cycle. So because this is a time, it is measured in seconds. For a symbol, it gets the uppercase T because we're talking about a specific time. When we've used a lowercase t before, it's usually been generic, how much time has elapsed. And we'll still talk about that with waves. So to distinguish between how much time has gone by and the specific time for one cycle, we need to represent that with an uppercase T. The other thing that might be interesting to look at, and that it is very closely related, is the frequency of a wave. And where the period is the time for one cycle, this is going to be the opposite. How many cycles in 1 second. So I've flipped these two words around. So the frequency as a symbol, little f, is just 1 over the period. It's the mathematical inverse as well as a linguistic inverse here. So it's units, then 1 is just a 1. Seconds was on the bottom here. If I think about the units of 1 over t, that's kind of a funny unit, 1 over seconds or cycles per second. So this gets renamed as the hertz, H-E-R-T-Z. And what determines the frequency of a wave is the source. If your wave is you sitting on the floor with a slinky, the source would be your hand moving back and forth. Or if this was a sound wave, the source would be a tuning fork or the musical instrument or whatever the source happens to be. That frequency is determined by where this wave is originating from. So the last property to define then is the wave speed. So if we start from a very generic definition of speed, as being distance over time, for lack of a better way to phrase it, and we think about distance in time in terms of the quantities we've just defined, our wave is going to move a distance of 1 wavelength in a time of 1 period, because a period is defined as the time for 1 cycle, and the wavelength is the 1 point until the points where the cycle starts to repeat itself. If I think about it in those terms, and I separate these a bit, this would be the same as saying the wavelength times 1 over the period. And 1 over the period was just the frequency. So as an expression for the wave speed, as a way to calculate it, I have v equals lambda times f, or speed equals wavelength times frequency. Now the important thing here is that the wavelength and the frequency are not determining the wave speed. They are a way to calculate it, but what the wave speed is determined by is what the wave is traveling through. So the wave speed is defined as how fast the disturbance or the wave is traveling through the medium. The medium is just the material that is present. So this could be sound moving through the air, and air would be the medium, or ocean waves through the water, and water is the medium. If you're imagining this like a slinky on the floor, if you have a slinky at home, I highly suggest you get it out and play with it. Tell your parents it's physics homework. If we imagine something like the speed along a rope, what that's determined by, as an example, is the force of tension on each end of the rope. You can imagine you're going to need a friend to play with the slinky and stretch it out and have one of you holding onto each end, divided by something called the linear density. So that looks kind of funny because it's a Greek letter rho, with a subscript of a cursive L for linear density. We're used to thinking of density as mass divided by volume, as probably what you're most familiar with. What we mean by linear density here is the mass divided by the length of the object. It doesn't really make sense to think about the volume of a rope, and that third dimension is pretty much negligible when it comes to something like a rope or a slinky. So it's just defined in terms of the length. Now there is an exception to this rule: how fast the disturbance is moving through the medium. And the big exception to this rule is electromagnetic radiation. EM radiation does not need a medium to travel through. This might sound familiar from looking at methods of heat transfer in Science 10, convection, conduction, and radiation. One was through a solid, one was through a liquid, or a fluid rather, and radiation does not need an intermediary. So light waves and electromagnetic waves of all kinds can travel through empty space without any intermediary. So there is no medium for electromagnetic radiation, and it has a set speed. And because this is a particularly important quantity in physics, it gets its own symbol of a lowercase c. C equals 3 by 10 to the 8 meters per second. I highly recommend that you memorize this number because it will come up a lot. So you've seen this diagram before, the different kinds of electromagnetic radiation. They all travel at this wave speed of 3 by 10 to the 8. The only difference between the different types that are mentioned in this row here in the middle are the frequency or wavelength. So our visible light spectrum is in here. And then over to the right, we have things with a longer wavelength. They have lower energy, infrared, microwaves, radio waves. And moving the other way with a shorter wavelength or higher energy, we have ultraviolet, X-rays, and gamma rays. One quick note about radio waves over here. This is not sound waves. This is a question that comes up often and a mistake that students frequently make. Radio waves are like what your radio in your car will receive. They are a form of electromagnetic radiation, and they're not sound waves. So there's a key distinction there. One travels at the speed of light or the speed of EM radiation in a vacuum. One does not. So if we want to look at a picture of sound waves, or a few pictures of sound waves. These are just two images to distinguish between a pure note. This is something that a tuning fork would make, or a musical instrument that's well tuned, versus noise, something like hitting a hammer or dropping a book on a table. One is a very pure frequency, and this noise is a mix of all kinds of frequencies put together so that it doesn't sound just like a straight tone. In these pictures, we have 4 here to compare and contrast the effects of amplitude and frequency. So what I want you to do is pause the video for a second here and take a look at these 4 pictures to think about what kind of an effect does frequency have and what kind of an effect does amplitude have on the properties of that sound. Okay, so we're looking at what these different properties, amplitude and frequency, mean about sound waves. So from the top row to the bottom row, we're looking at the difference between a high pitch and a low pitch. That would be what note it sounds like. And then from the left to the right, we have the same pitch, but we're looking at a volume, or the effect of that amplitude. So if I was going to summarize this, with sound, the amplitude does tell me how loud it is, or volume. The frequency is going to tell me the pitch, or what note it is. If I was going to think analogously for light, the amplitude is going to tell me the intensity, and how we would colloquially describe this is brightness. And the frequency is going to dictate the type of electromagnetic radiation. Within visible light, this would be about color, but we're just looking for now the general EM spectrum and not specifically at light.